Okay, so to finish this question up, FPX should be 388.98, and then you do the y direction, and so you're solving for FPY, take the others over, and it'll be FTY, FG of the beam, FG of the sine, both of those are going down, so they're negative on one side, take them over and they'll be positive, so FG of the beam, MG, plus MG of the sine, minus FT, y, which when you look should be sine theta. Okay, and then fill your numbers in. So FPY should equal, the beam was 3.5 kilograms times 9.81 meters per second squared, plus the sine was 24 kilograms, 9.81 meters per second squared, and then minus the tension was 463.81 newtons, sine of 33. And when you type all this in, you should get 389.36. 389.36 newtons. And remember, this will be the x, this will be the y. So now you want to find F of the pole. So square your x component, which is big, your y component, which is little, add them together and get FPY. Oh, I think I just wrote the wrong one in there. That's 3. This one, FP, is 389.36. See what happens when I do the answers when I'm not with you and then I screw it up. When you do all that one, the FPY is really much tinier. It's 17.17 newtons. So square this, square your 388.96, get 389.63, find the angle, and it's going to be tiny again. So at 2.53 degrees. And again, it's going counterclockwise, CCW beam. And the answer in the back of the book for this one is wrong, in case you were looking. Okay, so that's the end of the homework. One new piece, one new type, and it's actually example 3 on the sheet that we had from Friday. So the back side of the sheet, and it's a ladder. Okay, so here's my building, here's my ladder, and my ladder's leaning against the wall, okay, of the building, or the tree, I don't even, Okay, so ground, building. So it's a 10 kilograms, so the mass of the ladder is 10 kilograms, and it's 5 meters in length, so this whole length is 5 meters. Rests against a house, making an angle of 60 degrees, so the angle down here is 60. A 60 kilogram person, so the mass of the person, 60 kgs, climbs 3/4 of the way. Sorry, just couldn't see the number. So FG of the person is here. 3/4 of the way up the ladder, so this distance is 3/4 of 5 meters before the ladder begins to slip. What must be the coefficient of friction between the base of the ladder and the ground, assuming no friction at the top? Okay, so the ladder's uniform, so the FG of the ladder will be exactly halfway along its length, and the FG of the person is further up. So we have the two weights acting, but what are the other forces on the ladder? Well, the ground better be pushing up, because if it isn't, you're not going to be getting very far. So we call this F normal of the ground. So capital F, and then subscripts are NG for the ground. And then if there's friction at the base here too, unless you've set it up on a piece of ice. And to figure out which way the friction must act, think about which way would the ladder slip. If you were climbing it and the ladder began to slip at the bottom, which way will it slip? Well, it should slip out, which means friction should be acting in. So F, friction of the ground, would be down here, okay, acting that way. Then at the top, the house or whatever it's leaning against must also be pushing out. And so this is F normal of the house, FNH. That's why we did normal of the ground down here. And in reality, there would be a friction up here too. Again, if the ladder were to slip at the top, which way would it slip? Down or up? It should slip down. So the friction at the top would be acting up. So F friction of the house. But for now, until we get to another day or two, we will always assume this friction of the house is 0, and that's why it says assuming no friction at the top of the ladder. Okay, so we want to find the coefficient of friction. So we're looking for mu down at the ground. So we can start with the sum of the torques, and the sum of the torques should equal 0, and there'll be a torque from every force. So a torque from the normal of the ground, a torque from friction of the ground, a torque from normal of the house, a torque from the ladder, a torque from the person. Now the question is, where do you want to pick your pivot point? And I would highly recommend to always pick your pivot point down here at the base of the ladder. It's true you could pick it anywhere, but it'll be easiest if you pick it down here. One of the reasons it'll be easiest if you pick it down here is because then the normal of the ground and the friction of the ground go to 0. And so we'll be left with just 3 torques. Hold your writing utensil at the pivot point. Normal of the house is going to make it rotate counterclockwise. The weight of the ladder and the weight of the person clockwise. So it'll be positive, negative, negative. So it'll be R of the normal of the house, F normal of the house, sine theta normal of the house, minus R of the ladder, FG of the ladder, sine theta of the ladder, minus R of the person, FG of the person, sine theta of the person equals 0. Okay, when you look at this, none of the angles go to 0, so you can't do that. But really, we can find everything except F normal of the house. Now, it's not what the question asked. The question asked for friction, but you're going to get that eventually. We're going to have to do some of the forces as well. And if you wanted, we could stop here and we could go there so I could show you. So you could have started with some of the forces in the y is equal to MAY, and there's no movement in the y. And so it would be F normal of the ground, and it's positive, minus FG of the ladder minus FG of the person equals 0. And so F normal of the ground will equal M of the ladder G plus M of the person G. Why do we care about F normal of the ground? Because we're looking for friction of the ground, and so coefficient, so usually we need the normal. So ladder is 10 kilograms, 9.81 meters per second squared, plus 60 kilograms, 9.81 meters per second squared. And so we get an F normal of the ground to be 70 times 9.81. So 686.7 newtons. Okay, so we have our normal of the ground. If we go to some of the forces in the x, then, in the x, there's friction on the ground, so it's going to be 0. There's friction on the ground minus, the normal of the house. So what we find here is that friction on the ground equals the normal of the house, which takes me back then to here, because here we can find normal of the house. So that's why we're looking for normal of the house up here, and I'm going to run out of time. Shoot. So move these two over, R of the ladder, M of the ladder, G, sine theta of the ladder, plus R of the person, M of the person, G, sine theta of the person, divided by R normal of the house, sine theta normal of the house. So F normal of the house equals R of the ladder. Told us it was a 5 meter long uniform ladder, so the R should be half of its length, 2.5 meters. Mass of the ladder, 10 kilograms, and here's the important part, the angle between the R